Hello, everyone, and welcome to AISC Night School 17. This is the 5th session overall, and the first session on the second topic of this course, the design of facade attachments, presented by Alex Zimmer and James Parker. So welcome back to many of you, and welcome to those of you joining us for the first time. Today is July 16th, 2018. My name is Nate Goner with AISC Continuing Education. I will be moderating this night school session. I would like to introduce you all to today's speaker, Alex Zimmer. Alex Zimmer is a senior project manager at Simpson, Gumpertz & Hager's Waltham, Massachusetts office. He joined SGH's structural design group in 1998, and he designs new building structures with a focus on academic and healthcare buildings. He also investigates and rehabilitates existing buildings and other structures. Alex's experience ranges from the investigation of the collapse of a 100-foot-long suspended scaffold at the John Hancock Center in Chicago to the rehabilitation of an 80-year-old parking structure. More recently, he has served as the project manager and lead designer of a large hospital facility in Vermont and a new residence hall for MIT. Alex worked with SGH senior principal James Parker to develop AISC's Design Guide 22 on facade attachments to steel-framed buildings, and has presented a seminar on the topic for AISC in cities around the U.S. Alex earned his Bachelor of Science degree in Engineering from Swarthmore College and his Master of Science degree in Structural Engineering from Stanford University. Alex, thank you for being here today. I will now turn the floor over to you.
Thank you, Nate. Hope you can all hear me, and thank you for joining me this evening. I'm looking forward to this presentation on facade attachments to steel frame buildings. To give you a little bit more background about me and what I typically spend my days doing, I typically design new building structures. This is a small one-story building in the University of Maine at Augusta. It's the Holocaust and Human Rights Center there. And while it looks like these pedal shells that you see here in the image might be precast concrete, they are in fact curved tube structures with some wood framing between them, clad in copper. More recently, I've been working on a hospital at Burlington, Vermont for University of Vermont Medical Center, and this is their new Robert and Holly Miller inpatient bed building. It's a structural steel frame building designed for an additional 5 stories in addition to what you see here. At SGH, we do new structural design, but I have a group of colleagues who also specialize in building envelope systems, and we get to know facades up close and personal. And so as we were developing this design guide a number of years ago, we collaborated with our building envelope brethren to develop some good criteria for you. We also do things like water testing, and we also investigate a number of building structures like this transitional masonry with corroding steel inside a masonry system, which leads to cracking expressed on the outside of the building, such as you see here. And of course, there are projects in which the facade and the structure are integral, such as Simmons Hall at MIT, which we designed a few years ago. So what really is the problem here? Well, as we were putting this together a number of years ago, AISC was hearing some things from its constituency about problems with facade attachments, everything ranging from design coordination to excess RFIs and delays in the shop drawing process, delays in execution, to out-of-tolerance erection and perhaps even performance of the envelope and structural issues associated with that. And so in response to these, my colleague James Parker, who is in our Los Angeles office now, developed Design Guide number 22 back in 2008. And so the objectives of that design guide were to assist the practicing structural engineer in achieving things like slab edge spandrel beam designs for steel frame buildings that are structurally sound, that are durable, that are economical for the owner in the construction process, and that are accommodating of the different facade type requirements. So the objective of it really isn't to emphasize a preferred set of details, and I'm sure there are many different ways that you could modify the details that we're going to be showing you over the next 4 sessions here. But it's really to give the designer some guidance on how to make those attachments to the steel frame. So we're not going to be giving you a preferred set or prescriptive set of details. But hopefully you'll be able to apply some of what we discuss here to your own practice. So here's our syllabus for the next 4 sessions. Tonight we're going to be talking about the fundamentals of facades. We'll talk about design criteria. We'll also talk about design and execution responsibilities of those responsible for specifying, designing, and building these systems. We'll talk a bit about thermal bridging, which was not originally included in the design guide number 22. We'll talk about planning for clearances and also accommodating those tolerances in our designs. In week 2, next week, I'll be talking more about traditional masonry cavity wall systems, panelized facade systems, aluminum glass curtain walls, and how to size joints in these systems for vertical movement. 2 weeks from tonight, I'll be talking about slab edge design, spandrel beam design, and I'll touch very briefly on cladding supports that are away from floor levels. And 3 weeks from tonight, my colleague James Parker will be talking about accommodating lateral drifts in the facade systems, not only due to in-plane movements, but also to out-of-plane movements. And he'll have some guidance on what to do when you have conditions at building corners, which can be some of the most challenging conditions. So let's dive right in and dig into the fundamentals of facade performance. It's important to remember the building envelope doesn't just make the building look pretty. It encloses the building, it controls the transmission of air, water, heat, sound, and light both into and out of the building, and comprises a number of components. So it's not just the cladding itself, but it's the roofing, it's the windows, it's the doors, it's the below-grade waterproofing, and it's the interfaces between all of these systems. I think it's kind of fun to take a look back at the history of building enclosures. We've got a long history for millennia of designing load-bearing masonry walls, followed by a relatively short period of which we call transitional masonry, which I'll talk more about in a few minutes, followed by, from roughly the mid-20th century on, what I'm going to refer to as non-bearing or curtain wall type enclosure walls. So looking back at our millennia of experience with this kind of system, and I should add it's still used today, in these kinds of systems, the walls are typically fairly thick. The walls support all the loads of the building, whether those are lateral loads due to wind or seismic events, and they support the gravity loads as well. So the floors ride on top of the walls and move up and down as the walls expand and contract with changes in temperature and moisture. From an envelope performance perspective, the wall manages the moisture as a reservoir, wetting and drying. The thickness of the masonry really is what prevents the interior of the building from getting too wet. And so buildings of this period generally don't have a sophisticated indoor air or temperature control system. And of course, this presents challenges for buildings of this type that are being renovated that do have very tight air, temperature, and moisture controls on them. So skipping ahead to, let's say, the late 19th century, we have a transitional masonry period from about the period of late 1880s, 1890, up until about 1950 or so. And in these types of buildings, they have an internal frame system, but the exterior masonry walls are still thick. And they still function as a reservoir in terms of wetting and drying and protecting the interior of the building from moisture through their thickness. And in these buildings, the masonry is built tight against the internal steel frame, and the internal steel frame typically is designed to carry the gravity loads of the building itself. So in these systems, and I'll blow this up for you just a second, this is taken from a handbook of the construction from the early 20th century. In these systems, as you see here in this detail, the structural steel frame is built pretty much integrally with the exterior masonry skin of the building. Maybe it's a mixture of brick or stone and some terracotta or hollow clay tile. But in terms of its moisture performance, it really depends on the thickness of the masonry to protect the interior of the building from moisture and from temperature changes. And of course, this presents a problem because the moisture permeates the masonry and is in intimate contact with the building's steel frame. and that exposes the frame to moisture over time, which can corrode it, as you'll see in a second. And it also restrains temperature and volumetric changes of the masonry, as you see here in these two images. And as I mentioned, that moisture that's in the masonry is in intimate contact with the steel, which is probably not very well protected from it. Maybe it's coated in pitch, maybe it's painted, but over time that tends to deteriorate, and that leads to spalling and cracking of the masonry facade, probably at some later period of time. In fact, we're seeing a lot of buildings like this in our current practice here in the greater Boston area. So skipping ahead to the mid-20th century to what we're going to call contemporary curtain walls, and by this I mean any enclosure system that is not part of the structural system. It's hung or otherwise supported from the structure but does not resist the gravity loads of the structure. So the frame in this case carries the entire load of the building, not just the floors, but carries the facade loads itself. And the skin transfers the wind and seismic loads to the building frame, and the skin typically employs a drainage plane and some sort of backup waterproofing, although there are exceptions to that, as we'll see in a few minutes. So when we talk about what the performance requirements are from an exterior wall system, we expect that it's going to be able to accommodate the loads and deformations of the building frame, moving differentially to it, and that will transmit its loads back to the building frame. It needs to minimize water and airflow or vapor movement into and out of the building, and control heat gain or loss through some insulation between the skin and the interior. So breaking this down into sort of generic enclosure wall system, as you see here, we have a cladding system on the outside of the building. Interior to that cladding system is subdivided into joints to accommodate thermal movement and also to make it easier to construct. Inboard of that, we will have an insulation barrier, and inboard of that, we will typically have water barriers and air barriers that are mounted to a backup structure. Maybe that's cold form metal framing, maybe it's concrete masonry units, and some sort of interior finishes on the inside. In some systems, like in precast panel systems, one component can function in several different roles. So in the precast panel example, the precast acts as the cladding, it acts as the backup structure, and acts as the water barrier. And of course, the sealants in that kind of system are critical to its performance. In terms of insulation and thermal performance, building codes are demanding better and better performance from our exterior skin. And the structural attachments that have to penetrate that can create thermal bridges that can adversely affect the performance of the exterior skin of the building. And so for that reason, we are doing a lot of thermal modeling and moisture modeling to assess the consequences of things like these thermal bridges. And we'll talk more about thermal bridges later this evening. So when we design facades themselves, we obviously need to maintain structural integrity, and we need to maintain some provisions for movement of the facade differentially to the building structure. We need to consider the facade and system as a whole, considering the structural integrity. As I said, we need to provide provisions for movement due to wind, seismic, and temperature, and moisture movement. We need to think about the structural loads, and we need to think about the envelope performance. And by that, I really mean the water tightness and thermal performance of the building. So taking a finer view of this from not just the facade as a whole, but its attachments to the building structure, again, we need to think about the structural integrity of those specific attachments and connections, and we need to think about how they accommodate movement between the building and the facade. We need to think about the fact that they need to be durable because they're going to be concealed for probably the life of the building with little opportunity to inspect them and determine whether they're corroding or deteriorating. We need to make sure that those attachments account for tolerances in the building frame, erection, and fabrication, as well as tolerances in the facade material itself. We need to be thinking about how constructible these details are, and of course, we need to be thinking about the economy of them. How expensive are they to construct and erect? So when we look at things like structural integrity, we need to be thinking about the fact that there are competing interests that may be tricky to resolve. So for example, it's often desirable to support a panelized facade system at only 2 points for gravity load, because doing so provides a statically determinate system for our design and makes our analysis simpler and allows us to accurately compute the loads imposed on the base building structure. But doing that, having only 2 points of gravity support, makes redundancy difficult. In addition, the anchors that we need for good strength may not be very ductile. So it's really finding an adequate balance of redundancy, strength, and ductility. So in short, we have some conflicting ideas that we need to be able to satisfy. And these ideas conflict with others as well. For example, the thermal bridge issue that I was talking about earlier. We have to have some structure passing through the insulation plane that supports the gravity and lateral loads for the facades, but at the same time we want to make sure that we're not violating the thermal barriers of the building that would adversely affect the thermal performance of the building. First and foremost, the role of facade attachment is to provide a viable and reliable load path from the building enclosure, whatever that happens to be, whether it's aluminum and glass curtain wall or a brick masonry veneer, and transmit that load back to the building frame. And we need to think about supporting the gravity loads as well as wind and seismic loads. So the loads we need to think about, in summary, are the dead loads, in other words, the weight of the wall system itself. We need to think about seismic loads, whether those are perpendicular or parallel to the wall. Wind loads, primarily perpendicular to the wall, but parallel in the sense that they may cause panel joints to rack between individual panels of the facade. And thermal loads, due to the expansion and contraction of the facade systems themselves. So taking a dive a bit deeper into these, we need to think about the facade dead load itself and understand what that material is and how it likes to be supported. The dead load of the facade is usually a predominant gravity load on the facade, and most facades carry little to no live load, but be careful of facades that have projections like you see here, in which building maintenance workers could potentially walk or maybe hang a swing stage or a bosun's chair from. We need to make some estimate of what the actual facade dead loads are going to be when we're starting the design, and perhaps the facade hasn't been thoroughly designed by the architect at that point. And so some conservatism in our designs is usually warranted. Both ASCE 7 and the AIC Manual of Steel Construction give some tabulated weights of facade materials, and Table 2.1 of Design Guide 22 also gives some weights of facade assemblies. So in addition to calculating the gravity loads themselves, we need to think about where they're applied. They'll typically be applied eccentric to the building frame, and the designer needs to make a decision about where the hinge is between the facade system and the building frame itself. So for example, here as you see on the left, this is a precast panel, but it could be any panelized facade system. And there's a significantly different impact on the base building structure whether you assume the hinge is right here, where this bracket lands on top of the slab, or whether the hinge is here at the back side of the, at the back side of the panel. There's a fairly significant impact to the base building structure if we assume the hinge is here. We have to design the spandrel beam for considerably more moment, as well as the slab edge. And we'll talk more about this in upcoming sessions as well. When we design for wind loads, and I won't go into great detail on this tonight, it's really worthy of a much larger study than we're going to get into today. But we typically design for components and cladding wind pressures, which we derive from ASCE 7, most recent edition of which is ASCE 716, for which I'm showing you a chart here, typically for buildings of height greater than 60 feet. But of course there's the option to do wind tunnel testing as well, where the building is of a size that can justify the expense of a wind tunnel test. And quite often these tests will indicate that design pressures are lower than those prescribed by ASCE 7. And this can lead to a reduction in the cost of the cladding, and it can also lead to a reduction in the overall design forces on the main wind force resisting system of the building. When we look at wind pressures, we need to think about how those wind pressures and suctions act on the building and whether they're in combination with gravity loads. So typically, when we have negative wind suctions pulling away from the building, they may combine with gravity eccentricities to produce larger effects on the base building structure. And so it's often conservative to design for the suctions in these cases rather than the pressures, which tend to be lower. And it's usually conservative to do so. When it comes to seismic requirements, we need to look at a few different things. It's looking at the seismic forces, it's the relative displacements between floors, and it's making sure that our facade attachments are adequately ductile. And we have good positive anchorage between the facade and the base building structure so that you don't end up with conditions like the one you see on the screen here, which is from the Christchurch earthquake in February of 2001, in which the brick veneer essentially peeled away from the entire building frame. The real objective here is to make sure that the facade does not fall from the building frame and pose a risk to people who are trying to exit the building during or immediately after the earthquake, not necessarily to preclude damage from the facade. Now, when we design for seismic loads, every building is assigned to a seismic design category, which is a function of the risk category to the building, A being the least restrictive and relatively uncommon, to F, which is the most restrictive, which is for buildings of risk category 4 in relatively high seismic zones. And the objective here is to provide life-safe structures that are designed in accordance with the predicted ground motion at the site, as well as the risk to human life in the building itself. So when we design the facades attachments themselves, buildings that fall into seismic design categories A and B are typically exempt from having to design the attachments for seismic loads. Some notable exceptions are parapets, because they pose a fairly significant falling risk following an earthquake, and storage cabinets, which we're not obviously going to be discussing here in this series of presentation. When you get into seismic design categories C, D, E, and F, architectural components are not exempt from seismic design, and that's when we get into some of the slides that we'll be dealing with later here today. So when we design for seismic loads, it's typically computed using the force equation that you see here, which is based on an amplification factor, the seismic site seismicity, the weight of the component that you're investigating, a response modification factor similar to what you would use to design the base building structure, a component importance factor, which is a function of the importance to the building following an earthquake, and another term which represents the height of the components you're investigating with respect to the building site grade, how high up it is in the building. We also need to consider the relative displacements between the elements and make sure that we aren't having a pounding problem between different elements of the facade system. So we need to consider the limit states for design as we do this. The attachments must obviously be able to safely accommodate the forces that they are exposed to, and the joints between the facade systems must be designed to prevent hazardous damage, in other words, falling hazards coming from the building. But we don't really need to design everything for the full design loads when we're looking at things like serviceability, for example, when we're designing sealant joint movements. The designer needs to consider the consequences if the anticipated design loads or deflections are exceeded, but exceeding those design deflections may do something relatively benign to the building, such as damaging a sealant joint, as opposed to one of the more severe consequences, such as a panel falling from the building. So when we design for gravity loads using ASCE 716, there's typically based on the probability of exceedance of about 1 in 100. And we want to make sure that we don't design something with life safety implications exceeding this probability. But if we're considering the compressibility of sealant joints, which is typically not a safety concern, then perhaps we can increase the probability of the design load being exceeded in any given period. So take this equation, for example. This is a combination from the ASCE 716 commentary. and it has a 1 in 20 chance of being exceeded in any 1 year and a 92% chance of being exceeded in a 50-year period. So if the sealant joints on a building only have a life expectancy of, say, 10 to 20 years, then the probabilities of this load combination being exceeded might be acceptable to the owner, and that's certainly something to talk with the architect and building owner about when you're designing spandrel beams for deflection that may have an effect on the sealant joints in the facade system. When it comes to wind loads, IBC 2015 allows us to take some reductions in the strength design wind forces that are presented in ASCE 716. For most cladding elements, it allows you to take a reduction, multiplying your wind pressures by 0.42 for the components and cladding loads to determine the deflection limits for that facade system. Glass is a notable exception to this. You're only allowed to multiply those wind pressures by 0.6, typically. But the objective here, as we showed you in the last slide, is to reduce from the mean recurrence interval for strength design to a shorter mean recurrence interval, say 100 years, or something along those lines, which is more appropriate for serviceability considerations. And I should add that ASCE 716 in its commentary also includes some wind speed maps with reduced wind speeds, which are intended to do essentially the same thing, reducing the mean recurrence interval that one would use to design for serviceability conditions, such as building interstory drift or the design of joints. We also need to think about accommodating relative movement between the spandrel system or the base building structure and the facade itself. And we need to think about the fact that when we load the base building structure under the weight of the facade, it's going to deflect. The spandrel beam itself will deflect, it will rotate, and columns will shorten, brackets will deflect, and we need to be able to accommodate these and have adequate stiffness to limit those deflections so that we're not generating cracks in the facade that are aesthetically objectionable under normal loads. So when we accommodate these deflections, we need to think about how the facade itself is jointed or panelized into smaller subsections that are probably separated by things like sealant joints. The designer of the base building structure needs to ask the facade designer about the concepts and the strategies for the joints. So in this illustration, you see two larger panels, which as the spandrel beam deflects, a wide gap opens at the bottom of the panel, and the gap between the panels at the top compresses. Whereas if you have three relatively smaller panels and the spandrel beam deflects, you get a smaller opening of the gap at the bottom and a smaller closing of the gap at the top of the panel. So in the latter case, a lighter, less stiff beam may be adequate to support essentially the same facade loads. So some quick rules of thumb to consider when we design for stiffness. Typically, these can be based on rules of thumb, and in some cases by code provisions. So do we design our spandrel beam for the span over 360, or in the case of brick, maybe it's the span over 600 or 720, which would be recommended by groups like the Brick Institute of America. Or maybe we use 0.31 inches as the maximum deflection as listed in ACI 530. Or maybe it's 3/4 of an inch as recommended by AMA, which provides curtain wall guidance for aluminum glass curtain walls. But the controlling movement here that we're limiting for may actually be based on the compressibility of the sealant, which may in fact be more critical. So as a quick example, imagine that I have a building, in this case clad in brick veneer, with a 3/4 inch sealant joint between the brick above my shelf angle, which you see here, and the brick below the shelf angle. And I should add, if you can get an architect to go for a 3/4 inch sealant joint, you should probably look into a different line of work because you're a very effective negotiator. But imagine again that I've got a 3/4 inch joint and that I have the live load deflection. The maximum I can compress this joint to is about 50% of its original width. In other words, I can compress it down to 3/8 after deflection. And I need to accommodate about 1/8 of an inch for tolerance and for thermal movement, and so that limits the deflection of the spandrel beam under live loads, in other words, the loads that occur after the brick is in place, to about 1/4 of an inch, which for a 30-foot span is L over 1440, which is considerably smaller than any of these deflections that you see here. We also need to think about accommodating inter-story drifts between the different floors of the building. Although it's not codified in ASCE 7 or IBC, we typically use the story height of H divided by 400, or H over 500 for the inter-story drift between floors and for the building overall. IBC 2015 might limit the inter-story seismic drift to 0.025 H. In other words, about 10 times the wind drift. Now that varies depending upon the building risk category, but the point remains that the seismic inelastic seismic drifts will be much larger than the wind elastic drifts, as you can see from this example for a 12-foot story height. In addition, ASCE 716 requires that panel connections and the joints be able to accommodate at least 1/2 inch of inter-story movement. So it's not just the in-plane drifts that we need to be thinking about. It's the out-of-plane drifts as well, and how the facade system is able to accommodate those. So does the facade system deflect as a rigid body? In which case you get some movement like this, where the facade is relatively rigid and rotates about its supports? Or is the facade connection to the base building structure relatively rigid, in which case the facade is forced to undergo a double curvature bending between the floors as the upper floor displaces to the right? Or are there windows in the facade that effectively form hinges at the tops and bottoms of the facade system? These are all important things to keep in mind, and my colleague James Parker will be talking about those in some detail 3 weeks from tonight when we talk about designing for lateral movement. One quick word on restraint and how that can be inadvertently occur in our design. And we need to be thinking about how to prevent restraint from occurring. So it's very difficult to predict the forces in the structure that result from restraint of temperature from thermal and structural movements, and it's really best to avoid these types of conditions altogether. This is an example of a project that we investigated many years ago, which had an expansion joint between 2 different portions of the building, as you can see here expressed by the double columns. So this view is essentially a plan view. And the precast panel designer attempted to accommodate this joint by having a slotted insert right here that would intended to be to accommodate the movement of the 2 halves of the building, primarily due to wind and due to thermal movement. Unfortunately, this connection was torqued down too far, and ultimately, as the panel on the right attempted to move back and forth with respect to this shimmed connection, the bolt broke, and the panel fell from the building. So, and another reason why it's important as designers that we need to be looking at not just our own design, but say a delegated design of a precast panel supplier. We also need to think about the durability of our attachments. As I mentioned before, the attachments are going to be concealed once the facade is in place, and they'll be typically very difficult to inspect to determine if they are deteriorating or corroding somewhere behind the facade. So we need to think about what happens if the exterior wall leaks. How are our elements of that connection protected? We need to think about how likely the wall is to leak over time. In other words, where are the Achilles heels of that facade system? Is it in sealant joints? Is it in silicone sheeting? Where is the wall likely to leak? And how likely is the interior structure to come in contact with moisture? And we need to pay special attention to thin steel parts or steel fasteners that are unprotected, that may extend through the water barriers of the building. Remember, there's a good reason why we don't use corrugated brick ties anymore, because in those situations, water tended to accumulate on the brick ties and rust them out, and of course there's no way to inspect that until the brick falls off the building. Or you're perhaps doing a due diligence survey of the building and making some destructive openings, which nobody wants to do. So how do we protect the steel elements that are part of the facade attachment? Generally, designers will use hot-dip galvanized fasteners, or maybe they'll use stainless steel fasteners. Hot-dip galvanized fasteners have an advantage of being less expensive, more readily available, and field welding of these connections, although it requires removing the galvanizing locally, uses relatively more common welding procedures. And in these cases, the weld-affected areas should be touched up after galvanizing. On the other hand, the zinc coating may allow rust product to rip down through the facade if the zinc coating is compromised, and of course the zinc coating is sacrificial. It has a defined surface life, and so if your building has a long surface life and it's not likely to be reskinned at any point, maybe it makes sense to use stainless steel fasteners, which are more likely to perform better over time. But again, this is really the designer's judgment call, and something that the designer should discuss in consultation with the owner and the architect. So some problems that are associated with the support and anchorage. We can often have anchors that are positioned in a way that interferes with drainage through the wall system, anchors that may not be stiff enough to prevent differential movement for the facade system, and may tear the waterproofing and air barriers that are behind the facade. You can also have damage to barriers that occur during the erection and installation of the system that aren't caught for whatever reason. And of course, it's very possible to construct details that are very difficult to construct in the field. And of course, these all occur at the confluence of a number of different trades. It's not just the structural steel erectors, but waterproofers as well as perhaps carpenters and masons, or trades who erect the facade. A quick word on constructability and economy. This is a detail from one of my own projects, and I've included it here to indicate that you may be able to design a connection, but it may also be fairly expensive, and that's something to weigh heavily on the mind of the designer, whether the design that you've created is relatively economical. This is from one of my current projects where we were trying to achieve a thermal break between a canopy and a base building structure, which in this case happened to be cast-in-place concrete, and the red box that you see here is thermal break material. And so this is a very expensive connection, but it is in a critical portion of the building, and so that's why we decided to proceed with it. So we've talked about the fundamentals of facade performance. Now let's talk about the roles and responsibilities of those responsible for specifying, designing, and constructing facade attachments. So in detail, the owner will probably be responsible for giving some direction to the architect, who will ultimately be responsible for satisfying the owner's design criteria. And they will work collaboratively with the structural engineer of record for making sure that the base building structure is capable of supporting the facade loads itself. There may or may not be a specialty facade engineer responsible for the design of the facade connections themselves, as well as perhaps the backup structure for it. In fact, there may be multiple specialty structural engineers involved in the project. There may be a facade contractor whose work is directly supervised by a general contractor as well. So there are a number of different parties here that we should explore as we move on. Digging into the roles specifically, the owner is going to contribute to the facade performance requirements in terms of thermal and moisture performance. They'll have some role in the aesthetics, and of course, they hold the purse strings. They are responsible for maintaining the budget of the project and making sure that it comes in on their budget, working with the contractor to do so. They obviously will control the contractual relationships in most typical projects, typically holding the contract with the architect as well as perhaps the construction manager, unless it's a design build project. Ultimately, they will be responsible for maintaining the facade, making sure that it remains safe and that it does the job that it's supposed to do, and responsible for periodic inspections of that facade per local regulations. The architect, in turn, will then select a system that can meet the owner's project requirements, and they'll have a fundamental role in designing making the decisions that affect the facade attachment, such as its materials, its jointing patterns, and its thermal performance. And they'll select and define the attachment strategy in consultation with others who may include the structural engineer of record, a specialty facade engineer, or maybe the owner's facade consultants, manufacturers of the facade products, and the facade specialty contractors who are charged with erecting that facade on the building structure itself. So they really set the stage for the project. The structural engineer of record, in turn, must understand the facade attachment strategy and to be able to design the primary building structure. And they must provide the anticipated structural movements, in other words, the interstory drifts of the building, how much the floors are likely to deflect where the facades are supported, and give those structural movements to the rest of the design team. Obviously, they need to design the building frame and the slab edges that are consistent with the attachment strategy. And so it's really in the project and the structural engineer of record's best interest to consult with the architect regularly about the facade attachments. And while the structural engineer of record may or may not contract with the architect specifically to develop facade criteria, it's definitely in the project's best interest to do so, since that facade attachment strategy has such a significant impact on the structural engineer of record's work. In addition, the structural engineer of record should clearly delineate on the structural steel documents the items that will be designed by the structural engineer of record, as well as those that are delegated to a specialty structural engineer if there is one. They should indicate the assumptions and limitations of the facade attachments. For example, if there are specific loads that the base building structure anticipates or excludes, those should be noted. They should also indicate tolerances of the structural steel frame if they vary from perhaps what's listed in the AISC Code of Standard Practice. And those details need to provide sufficient adjustability to accommodate erection and fabrication tolerances of the steel frame, as well as the facade system itself. And we'll talk more about those later this evening. And when we get into contractors, there's probably a general contractor or a construction manager who's responsible for coordinating all the trades and making sure all of the submittals for both the base building structure and the facade system are submitted to the proper parties for review. And they need to review those submittals also for conformance with the project specifications. They, in turn, may delegate the design and erection of the facade to a facade contractor, typically done through the architect's performance specifications. And the facade contractor, in turn, will typically hire a specialty structural engineer responsible for the design the design of those facade components. That specialty structural engineer is typically, as I said, under contract to the facade contractor. And in fact, there may be more than one specialty structural engineer on a project. Perhaps there's one who's responsible for designing the exterior wall framing, typically done in cold form steel. And there may also be specialty structural engineers for the design of metal panels and or aluminum glass curtain walls or precast panels or thin stone veneer panels. So there are a variety of different specialty structural engineers that may come into play on any given project. That specialty structural engineer may or may not be responsible for the inspection of the facade components during construction. But again, one thing that I think I've emphasized a good bit here is that we really need to have good communication by all members of the design team, especially the structural engineer of record, and if there are specialty structural engineers, with those engineers as well. So let's take a look at several different types of facades and talk about who is typically responsible for those components. In the case of a masonry veneer system with field-laid brick, as you see here, the architect will typically specify the brick, probably the brick ties, and performance specify the backup wall, which is shown here as cold form metal framing. that design of cold form metal framing will typically be delegated to a specialty structural engineer, though that's not always the case. And the structural engineer of record will be responsible for designing slabs, the spandrel beams, elements that brace the spandrel beams, such as this kicker angle shown here, and any hangers and relieving angles or shelf angles that support the brick veneer. In the case of a story-tall precast panel, the architect will perform and specify what the exterior panel should look like and develop a jointing system for it. And then that design will be delegated typically to a specialty structural engineer who's responsible for the structural design of the panel to meet the structural design criteria. And that specialty structural engineer will also be responsible for designing the connections to the base building structure. Again, the structural engineer of record will design the spandrel beam, the slabs, and any structure that's necessary to support those connections. In the case of a column-supported precast panel that may span from column to column, again, the architect and specialty structural engineer will be involved in the design of the panels themselves. The specialty structural engineer will design the connections, such as this tie-back anchor to a column, as well as the gravity load anchors to the column, and also perhaps intermediate tie-back anchors which support lateral load from wind and seismic loads and transmit those back to the base building structure, as you see here at the top of the slab, and to this hanger, which is supported from the underside of the spandrel. And the structural engineer of record will need to provide structure to support those tie-back anchors. In the case of an aluminum glass curtain wall, it's a similar kind of approach where the architect will perform and specify the aluminum glass curtain wall system itself, the design of which will be delegated typically to a specialty structural engineer. And the structural engineer of record will design the base building structures, spandrel beams, and perhaps some brackets or clips to support the curtain wall system. So as a quick case study, this is a dormitory project I'm currently working on. It's a concrete frame building, but I think the principles that I'm going to discuss here are equally applicable to any other type of facade system with a specialty structural engineer. So in this case, it's thin brick supported on cold form metal framing studs, which are panelized and brought to the field and erected in panels. So as you can see here at the top, we're resisting gravity and in-plane lateral and out-of-plane lateral loads here at the top of the panel, and we have lateral restraints here at this lower floor level, but the panel itself extends more than 9 feet below the lowest elevated floor level, and that panel is not capable of supporting out-of-plane wind loads with a 9-foot cantilever, as you see here. And so we worked collaboratively with the specialty structural engineer for these panels, who was brought into the project very early in the process to design a system of lateral braces, such as you see here in green. This is a section view. We designed these braces to laterally support the panels out of plane, concealed above the ceiling height. So in summary, the thing to really take away here is that it's important that everybody communicate on the project. The facade attachments are difficult precisely because every member of the design team has a significant role in the planning, design, and coordination of them. And a poor communication will probably lead to poor execution in the field. So moving on to the topic of thermal bridges and breaks, this is a topic that Facade Design Guide 22, which was written about 10 years ago, barely touches on. At that time, we were just beginning to scratch the surface on it and try to understand how these affected buildings. Now that we're 10 years beyond its initial publication, the state of our practice has really changed considerably. Our first thoughts are, of course, safety and cost. But as the state of our practice changes, in my mind, for the better, we need to consider ways that the building design can do things like reduce energy use, improve occupant comfort, and reduce the likelihood of condensation on cold surfaces within the building's envelope. And before I go too far, there are 2 great resources out there that are freely downloadable to you from the web. I've shown them here. One is Thermal Bridging Solutions, Minimizing the Structural Steel's Impact on Building Envelope Energy Transfer. That was published by AISC back in 2012. And more recently, in May of last year, Northeastern University, with some of my colleagues here at SGH, as well as from Klepper, Hahn, and Hyatt, did a great research study published under the Charles Pankow Foundation on thermal break strategies for cladding systems and building structures. The Northeastern University study did thermal modeling of a number of unmitigated, in other words, not thermally broken connections, as well as mitigated connections, those with thermal breaks, considering a variety of proprietary and non-proprietary thermal break products. And they also did physical testing in the laboratory and thermal and finite element studies of a variety of connections, including lap-spliced bolted steel connections, slab edge supported shelf angles, and cantilevered canopy beams and rooftop dunnage frame posts. So I encourage those who are interested to do more reading on this topic. The Northeastern University study provides some great design recommendations as well, which I will summarize some of them here. So in essence, we are trying to make sure that we eliminate or reduce energy loss from the building through our facade attachments. We try to improve occupant comfort, and we try to reduce the risk of condensation within the building envelope that could lead to corrosion of fasteners that are not readily inspectable, as I mentioned before, as well as reduce the chances of mold growth inside the building envelope, which could lead to health hazards for the building's occupants. So on this slide, I'm showing a connection detail for a project I worked on about 12 or 13 years ago. This is a slab edge supported shelf angle for brick. You see the brick veneer out here with a relieving angle right here, or shelf angle, that passes through the purple insulation plane. So and this angle is effectively continuous. It draws heat out from the building through the line that you see on the facade here. This is not a great detail for thermal reasons, but it also has some adjustability reasons that we'll talk about later on. These days, we're typically trying to break these types of continuous connections, and there are a number of different ways for doing that. One is by using prefabricated assemblies, such as the one you see here. So this consists of a prefabricated steel plate with stainless steel bolts passing through an insulation shim, although this is relatively thick shim, attaching to a backup structure behind it. It is, of course, possible to build up these kinds of assemblies as well in the shop or in the field using thermal isolation pads, isolation bushings, thermal isolation washers or stainless steel washers, and stainless steel bolts. So let's take a closer look at that. This is from one of my more recent projects. Here you see a conventional carbon steel plate, unprotected because it's behind the moisture barrier of the building. The thermal isolation pad right here, which is designed to be in the same vertical plane as the insulation plane of the building. And then structural steel plate on the outside, but this is galvanized because it is beyond the moisture barrier. And passing through this, there are stainless steel bolts, 593 stainless steel bolts, and thermal isolation bushings that pass through this as well. Here's another look for a hung relieving angle assembly from another project I've worked on recently. Again, it's a conventional carbon steel hanger angle with a thermal isolation pad. And in this case, we used carbon steel welded studs welded in the shop to the hanger angle that passed through the thermal isolation pad. And there are bolts here on the outside with bushings through the holes. So this is designed for horizontal and vertical adjustment here at this connection as well. You might have noticed these look like they're skewed a little bit. That's because the hanger angles haven't been plumbed and aligned yet in this photograph. Another alternative to using this thermal break solution is by using a thermal insulation coating. These, however, are not true thermal breaks. Rather, they disrupt the heat flow along the structural steel path from the warm side to the cold side, effectively modifying the surface temperature to improve occupant comfort and reduce condensation and provide some measure of protection against corrosion underneath the coating. So this yellow material here is the thermal insulation coating, and it's applied to the shelf angle, which has not been, brick has not been applied to yet. The hanger angle and this gusset plate back here are also coated with that thermal isolation coating. Now, there are cases where putting some sort of thermal isolation coating perhaps just isn't practical for reasons of the load that's applied to the element or for other reasons. And this is another example for one of my recent projects, again, a concrete frame building transitioning to structural steel framing around a generator well on the building. And the overturning moments at the base of this column were simply too large for us to resist with a thermal isolation break right here where you'd really want it. And so what we ended up doing was applying local thermal isolation blankets around the structural steel columns that extend above the roofing system and tying that into the roofing insulation, which you see here in this bluish-green color. Obviously, when you're introducing a plastic material, whether that's reinforced or not, into the faying planes between two structural steel elements, we need to consider a few different things than we typically do in a conventional steel-to-steel connection. So in the thermally broken connection, you'll probably need to oversize the bolt holes a little bit, and that will result in some deflection. So even if you're using a standard 1/16 of an inch oversize, there's no clamping that really occurs in this connection. You can't rely on this as a slip-critical connection. So you'll have some slop, if you will, in the connection as the outer plies drop relative to the inner plies due to the 1/16 oversize, even in the standard bolt. You will also develop bending and compression in the thermal break material down here as the thermal break material compresses. You will also develop bolt flexure deformation as the bolt here is in flexure between the backup angle and the angle that you see out here. You'll also develop shear deformations in the bolt. So these are some additional deformations that affect how far the shelf angle that you see out here deflects relative to the backup structure and relative to the spandrel beam above it. So how do we design for these kinds of things? Well, the Northeastern study found that for relatively thinner insulating shims, less than about an inch in thickness, generally had less impact on the strength and stiffness of the connection than thinner shims. And I think that's a relatively obvious conclusion. And they verified this through some physical testing that we did here in our laboratory, as well as through some finite element analysis done using Abacus. And they concluded that while the bolts dictate the failure, the shim's influence on the overall behavior permitted additional displacement of the system and also decreased the connection stiffness. The Northeastern study recommended several methodologies for calculating the stresses due to direct tension in the anchors, as well as flexure in the bolts, and the compression stresses in the insulating material that's down here. So they developed a method for computing those compression stresses. For simplicity in designing of the bolts themselves, it may just be easier to base that compression force based on the couple of overturning moment divided by the distance between the bolt fasteners. So when we design the bolt fasteners, we need to consider not just the tension on the fasteners due to the tendency of this to overturns, but direct tension due to applied wind loads, as you see here. We will have shear in the bolts, and that shear results in flexure through the thickness of the insulation material. And the Pankow study recommended considering the bolts in single curvature cantilevering from the backup hanger angle, as you see here. So when you then check those bolts using AISC equation J-3.3a, combining shear and tension in the bolts, the tension component needs to consider direct tension to the bolts as well as flexure in the bolts through the thickness of the shim material. I'll summarize quickly some conclusions from the Northeastern study. They summarized that using non-conductive shims is a thermally effective means of mitigating the thermal bridges. That's because the non-conductive shims effectively provide isolation between the two steel components. They also found that FRP, in other words, fiber-reinforced plastic structural members, are very effective at thermal bridge mitigation, continuous as well as discrete cladding connections. And they used also some shelf angles, steel shelf angles with 3x4 shims installed to bolt locations to provide discrete cladding separation in the cladding backup system. They found a significant reduction in the area of steel in direct contact with the pour stop helped. So in other words, putting shims between a shelf angle and a pour stop really helped. And they also recommended reducing capping the compressive stress in the fiber-reinforced plastic to about 30 to 35% of the ultimate compressive strength of that material to eliminate the chances of creep over time. They also found that stainless steel bolts offer significant improvement on the thermal transmittance through the connections. They also found, which was a surprise to me, that thermally improved bushings offer relatively little mitigation benefit. So that's something that I'll be changing in my practice going forward, is to eliminate the bushings and to use stainless steel fasteners. So again, another case that may make sense to consider in the future is maybe using stainless steel elements rather than using a thermal shim. So maybe using stainless steel in the red zone and omitting the thermal break material. And now you can use a slip critical connection here that has higher strength and higher stiffness and lower rotation out here at the shelf angle. Of course, a lot of this has not been studied yet with regard to fire performance. The influence of polymers, temperature on polymers and thermal separators has not really been thoroughly studied yet, and we don't really know how these things tend to perform in the face of a fire. So that's something for future study. And the other thing we need to think about is whether the costs of doing this kind of connection really benefit the owner in an effective way. Does eliminating the risk of condensation and mold and improving thermal comfort and reduce energy use, is that really worth the costs and challenges of constructing connections that are like this? If it's a simple one-off connection that's, say, in a back of house area where it's not likely to affect the occupants, then maybe it isn't worth the effort. On the other hand, if it's an area that's continuous along the facade and is going to have a fairly significant thermal impact to the building, maybe it is worth considering. So let's talk now about accommodating construction tolerances and clearances. We need to be able to provide adjustability between the structural details and the facade attachment details to achieve a facade that's erected within acceptable tolerances relative to the theoretical plane. So we need to make sure that we can accommodate the erection tolerances and provide some clearances. And a couple of definitions as we get started here. When we're talking about tolerances, we're talking about the permissible amount of deviation from a specified dimensional criteria, such as a camber or a plumbness. When we're talking about clearances, we're talking about spaces that we purposely design into the building to allow for movement, to accommodate tolerances, whether they're from erection or from fabrication, and to provide some access during assembly. When we specify the frame tolerances, it's generally unreasonable for the designers to disregard the realities of common construction practices. Although designers can specify very tight steel frame tolerances to limit the amount of dimensional variability the facade assembly has to take into consideration, it's unreasonable to assume this steel fabricator and erector are going to be able to produce a structure that will have tolerances that are much tighter than those specified in the AISC Code of Standard Practice. Although many frames are erected well within these tolerances, requiring anything stricter should only be considered in exceptional cases and in consultation with fabricators and erectors local to the project. I will add here that Design Guide 22 includes a summary of fabrication and erection tolerances from the AISC Code of Standards Practice, as well as ones that are specific to a number of different facade systems. Also, the structural engineer of record really should note which items of the connections are intended to be adjustable on the construction documents. So in terms of the types of different tolerances. They're material production tolerances, such as you might find in the sweep of a beam or the allowable deviation in thickness of an architectural panel. They're fabrication and assembly tolerances, such as the allowable variations of subassemblies of facade, such as prefabricated panels. And then there are erection and installation tolerances, such as the plumbness of a column or the location of a column in plan, or where the facade panel gets erected relative to a slab edge. And these three types of tolerances are aggregated together into accumulated tolerances. And it's these accumulated tolerances that we need to consider in our design. Now, it's unlikely that all of the tolerances will stack up against you to the maximum in a way that is completely unbuildable, that they'll all accumulate in the same direction. A perfect storm, if you will. The problem, however, is understanding how the deviations aggregate in a way such that you can accurately plan for them, and that is really something of a guess. The designer cannot know how much the sum of all of these different tolerances will aggregate in reality in the field. And there's no statistical data that's really available to us as designers to guide us through this. So let's take, for example, a quick case study. Imagine that you have a precast panel that's supported at the columns at the 10th story of the building. That precast panel spans laterally 40 feet between adjacent columns. At the 10th story of the building, the column by AISC Code of Standard Practice can deviate 2 inches inward toward the building or 1 inch away from the building. And the spandrel beam spanning between those 2 columns, which is going to have a lateral tie back to the middle of the panel, can sweep in or out 1/2 inch. From the PCI design handbook, the plan location at each end of the precast panel could deviate plus or minus 1/2 inch. And the precast panel can bow up to L/360, or in this case, plus or minus 1.33 inches relative to its theoretical center line. So, and in this example, we're going to ignore the variability of the actual location of the columns. So we're assuming the columns have been erected in exactly the right spot in plan at the base. And we're talking really here only about the deviation of columns due to plumbness. So if we look at what we're interested in here, it's the gap between the back of the panel and the column, that's this dimension here, as well as the gap between the back of the panel and the spandrel beam, where we'll have a lateral connection for out-of-plane wind and seismic loads. So if we add all of these deformations together at the columns, the column could be out 1 inch or in 1 inch, and the plan location of the precast panel could be 1/2 inch out or 1/2 inch in. So the gap between them could open by 2.5 inches or close by 1.5 inches. At mid-span, where we have to contend with the sweep of the spandrel beam as well as the out-of-plane sweep of the panel, things get a little bit more interesting. We have 2 inches out from the column plus 1/2 inch out from the panel location at the column, plus 1/2 inch of sweep on the spandrel beam, plus 1.33 inches on the panel bowing. So that gap could open by 4.33 inches, or it could close similarly by 3.33 inches. So when we start to add these up, and you look at what the theoretical gap is and see how they close, we end up with, at the column, the largest gap, if we planned on a 2-inch initial gap, the largest gap could be the initial gap of 2 inches plus 2.5 of 4.5 inches out. The smallest gap, if you had 2.5 inches closing by 1.5 inches, you would end up with a 1/2 inch gap. At mid-span, if you started with a theoretical 4-inch gap between the spandrel beam and the backside of the panel, the largest gap could grow to 8 1/3 inches or reduce to 2/3 of an inch. So graphically, what does that look like? Something like this. At the column, you end up with a very small gap, and in the mid-span, you end up with a very large gap due to the bow of the panel and the sweep of the camber beam, combined with the column location as well as the panel seat location. So there really isn't any great science behind it, but some designers look to the sum of squares method for determining the largest and smallest gaps. And you recall that we have 1.5 inch a reduction in column location as the column moves in of an inch, the panel moving in half an inch, or column moving out 2 inches, panel moving out to half an inch. If you do the squared sum of squares, you might be plus or minus roughly 1 to 2 inches. Now, in the middle of the panel, that starts to reduce from what we saw in the previous slide of 8.33 inches to 2/3 of an inch. Realistically, maybe you'll get something on the order of minus 1.8 inches to plus 2.5 inches. So that seems to be a bit more reasonable. And for the enough variables in the mix, the square root of sum of squares starts to approach a normal distribution if you were to do a probability assessment of this. So there's no great science to this, but this is one possible method that you could employ to try to get a grip on deviations from the design tolerances. So some recommendations for dealing with this are to understand the sources of variability from the structural steel frame, as well as the facade system itself, to try to understand the consequences of exceeding the tolerance and providing provisions in the details to accommodate that, and understand the costs associated with providing the means to accommodate that variability. Moving on, for each project, at the beginning of the project, we suggest the team develop the design criteria for addressing these accumulated facade tolerances. So, for example, decide on the target amount of adjustability. Are we going to use something like the square root of sum of squares method? Are we going to follow AISC frame erection tolerances, or do we need to specify something tighter than that, which I would recommend that you not do if you can avoid it? Try to make some qualitative or quantitative assessment of the consequences of the different variable tolerances here, and based maybe on your experience and judgment, and decide which elements of the facade attachments will be adjustable, and by how much, and by whom. And I think it's really in our best interest as the building designers to have open and honest communications about these tolerances with everybody that's involved in the project team, and how they're going to be accommodated and who's going to be responsible for that. When it comes to designing joints, one quick reference here to ASTM C1472, which provides some guidance for calculating joint widths and other movements, and we'll be touching more on this next week. But it's important to realize that this is a good reference for you going forward. And now for a quick case study from one of my own projects. This is a architectural cross-section through a steel frame building. The base building structure is back here. We've got some thermal insulation here. We've got a aluminum glass curtain wall system, which you see here. And here you see some structural steel elements penetrating through the plane of the aluminum glass curtain wall and supporting a sunshade on the exterior of the building. So this is the architectural section. This is our structural section. So we had some HSS hangers and horizontal elements, which we intended to have a WT section knifed into in the field. That was to be field welded for in and out of plane adjustability. We had some means to adjust the location of this perpendicular to the plane of the page at the top connection of this. And here you see a thermal isolation pad right here, which I will attempt to highlight for you, right in there. Sandwiched between a structural steel WT as well as a structural steel plate on the outside with stainless steel bolts passing through that. And then all of this structure that you see out here is structural steel HSS sections that are galvanized because they're beyond the building envelope. In the end, this is what we ended up with in the field. And this channel, by the way, is this gutter that you see right here. So this is now looking from the outside of the building. This is the gutter. This is the standoff. These are the stainless steel bolts that pass through the insulation plane, and behind this is the structural steel backup and hanger system. And here you see the aluminum glass curtain wall. So unfortunately, the erection sequence for this project ended up not going the way that we had intended it going because the building needed to be enclosed sooner and there had been previous delays in the project. And so the aluminum glass curtain wall ended up getting erected long before any of the any of the structural steel sunshade structure. And so all the glass was in place before any of this hardware that you see here was erected. And so we ended up with some fairly large deviations from our planned locations that we had to accommodate, and having to do a lot of welding in the field very close to the glass curtain wall system. So even the best intentions can go awry on you. So some key takeaways as we wrap up here. It's important that the design team develop a strategy early in the project for supporting the facade elements from the base building frame. And given the strategy, it's important the design team communicate the responsibilities and scope for each of the elements of the facade system. Who is going to be responsible for which elements, and which elements are going to be shown by whom on their drawings, whether that's the architect, the structural engineer of record, a specialty structural engineer, or a facade contractor. The structural engineer of record needs to understand how the building is going to be supported, what strategies the architect plans to use to panelize the facade system, and where those gravity and lateral supports need to be, and how those get transferred to the primary building frame. The structural engineer of record needs to communicate relevant frame performance characteristics such as out-of-plane deformations and vertical deformations to the rest of the design team. And the structural engineer of record needs to strive to develop slab edge and spandrel beam designs that are consistent with the facade attachment strategies developed early in the project. The design needs to be accommodating of tolerances, as we've discussed earlier, to accommodate facade movements due to thermal, due to gravity loads on the base building structure and on the facade itself, and that those tolerances need to be communicated clearly and accepted through all members of the design team. The structural engineer of records documents for the primary building structure should indicate pertinent assumptions about the facade attachment so there aren't surprises later during construction. And the project documents should indicate who's responsible for the facade design and the attachments and all performance requirements. And last but not least, the steel frame will often be fabricated long ahead of the final facade attachment design and the detail. So we need to make sure that the primary frame is detailed accordingly to accommodate possible variability in the facade attachment design. The steel frame detailers and the fabricators are not the coordinators of the facade attachment details. So the design team needs to do those up front and do their best to make sure they're coordinated. And also the design team needs to review the shop drawings that come back from those facade contractors to make sure the design of the facade elements is consistent with the base building structural design. And with that, I think we have time for some questions, Nate.
Hi, Alec. Thank you. Yes, we do have some time for some questions, and we have some questions to go through here. And as a reminder, you can submit those questions in the chat feature on the left-hand side of the screen. But before we get into some of those questions, we do have a couple of interactive polling questions to test the audience's knowledge on some of the concepts that you presented, Alec. The first polling question is this, and the audience can participate by clicking on what they think is the correct answer on their computer screens. This question is a true or false question. True or false, the structural engineer of record and/or the architect should indicate on construction documents which elements of the facade attachments are to be adjustable in the field. Is that true or false? Again, the structural engineer of record and/or the architect should indicate on construction documents which elements of the facade attachments are to be adjustable in the field. A few moments for everybody to have an opportunity to participate. Close the poll. All right, Alec. It looks like the audience overwhelmingly thinks that this one is true. Did they get that right?
They did. That was one of the key takeaways of this, that we as the designers of the building need to indicate which elements we think should be adjustable and give some guidance on how to do that.
Right. Good job, everybody. So one more interactive polling question to get through. Which of the following is not typically part of a built-up thermal break assembly? Is the answer A, thermal isolation pads, B, thermal isolation bushings, C, carbon steel bolts, or D, thermal isolation washers? And again, the question is, which of the following items is not typically part of a built-up thermal break assembly? All right, so getting a few last responses here. Goes in the poll. All right, Alec, it looks like about 90% think that carbon steel bolts are not typically part of a built-up thermal break assembly. Did they get this one right?
They did. That is true. Carbon steel bolts are pretty good conductors of heat from the interior of the building to the exterior, or cool air from the or drawing in heat from the outside. So we tend to recommend using stainless steel bolts in these applications. Now, I noticed some people said thermal isolation washers, which we can use underneath the nut of a stainless steel bolt. We do sometimes use those. It's also possible to use a stainless steel washer, but the correct answer in this case was C, carbon steel bolts.
All right. Well, thank you for that response. We're going to go ahead and get into an open question and answer time here, as much as we have time for. And the first one, we have actually a few questions on this application of these thermal break assemblies. And the first one we'll look at is slide 96.
Okay.
So you mentioned these additional deflection and rotation sources. The question is do you, in your practice, typically explicitly check the deflection, or make sure that a specialty engineer is checking the deflection of the fabric pad?
Yeah, we do look at the compression of the reinforced pad that separates it. You'll get a very small amount of compression typically if you're designing for only 30 to 35% of the ultimate compressive strength. However, it's not really so much that you get a large deformation of the pad, so much as that you get a rigid body rotation of all of the elements that are outboard of it. So if I can get my green arrow here, this assembly will undergo, in addition to its own flexural deformation of the horizontal leg of the shelf angle, all of this will deform as a rigid body due to the compression of the thermal pad here. So it's something that you probably should be considering in your practice. And as I mentioned, the Northeastern University report gives some guidance on estimating the deformation of that thermal pad.
Right, thank you. Next question, also on these thermal pads. Do you know off the top of your head any idea of what the compressive capacity, you mentioned here, ultimate stress capacity, is typically on these pads? And also, what types of typical E values do these pads have?
I unfortunately don't have those off the top of my head, though I suppose it would be a good thing for me to look up, and I'm happy to respond to that afterward. I'm pretty sure they are cataloged in the Northeastern University report.
Right. Okay, next question. This detail on slide 95. Mm-hmm. So with this application of the local insulation blanket, you still have a thermal bridge represented by this steel plate, anchor plate, into the concrete.
That is correct. You do. In this case, the steel column was effectively a moment frame above the cast-in-place concrete structure below, so we were unable to use a thermal break assembly here between the steel column base plate and the cast-in-place concrete structure. So yes, there is a thermal bridge here. However, it's possible to do some thermal modeling on a case like this that looks at what the effective heat transfer is through the structural steel element down into the concrete structure. And in this case, there is a detail I have not shown you here is there's a ceiling above this, so which will also tend to trap heat on the underside of the concrete structure. So in this particular case, we weren't concerned about it. We convinced ourselves that even though there is a thermal bridge, in theory, the consequence of it is minimal, and we weren't getting that much heat transfer through the steel column.
Okay. Next question. You discussed this concept of accumulated tolerances and that it's unlikely that all tolerances will kind of add up in a worst case scenario. Do you ever feel moved then to kind of put a maximum on the accumulated tolerance in your construction documents?
That's a good question. I have never done that explicitly, though I suppose that one could. Effectively, you may do that depending upon your facade system. So, for example, if you had a brick shelf angle that is hung from the spandrel beam using hanger angles or channels or something like that, you may effectively do that through the lengths of the slotted holes that you provide in the erection bolts, and that's how we would typically do it. And I've had cases where things have been erected out of tolerance, and those hanger angles have had to be unbolted and field welded in place, or I've had cases where I've had to have a longer shelf angle horizontal leg installed. Not ideal conditions, but it does happen. But effectively, in case of a brick veneer system, you probably are effectively specifying what that is through the lengths of the slotted holes in your adjustable connections. In the case of a precast panel, maybe it does make sense to indicate what you anticipate the out of tolerance of the panel is, at least to put the contractors on notice that this is what you, as the designer of record, have considered in your design.
Right, going back a little bit in the presentation, you were discussing some roles and responsibilities on some various typical types of exterior walls. The question is this about the case of metal stud exterior walls. Who typically, do you know, is responsible for designing wood blocking for those types of walls?
That's a good question. I suppose it depends on what the purpose of the wood blocking is. If you're using the wood blocking to resist compression flange buckling of the steel studs, that's probably in the court of the specialty structural engineer. I suppose it really depends on what the purpose of the wood blocking is. If it's to support fixtures that are attached to the inside of the wall, that's probably shown on the architect's drawings and effectively designed by them, though probably not designed by the specialty structural engineer.
All right. Well, thank you, Alec. That's actually all the time we have for questions right now. If there were a few questions that we weren't able to get to, if you did not have your question answered, rest assured that we did receive all those questions, and we'll be following up with Alec and working with him to provide email responses in the coming week.